When you're talking to a sophisticated tool, maybe a large chatbot like ChatGPT, it doesn't just return data. It feels like it's, well, constructing arguments. It feels like genuine comprehension almost human.
It really does, doesn't it? But it's kind of the ultimate linguistic illusion. The magic isn't actually understanding, not like we understand things. It's fundamentally an engine of statistical prediction. And today we're going to dive into the 10 core concepts, the essential vocabulary, really, that make that unbelievably sophisticated prediction possible.
Welcome to the deep dive.
Yeah.
Yeah, if you spend any time in, say, AI meetings or tech discussions lately, you know the feeling. Jargon just gets tossed around. It's like technical confetti. RAG this, attention that, vectorization. It can be pretty overwhelming.
Absolutely. So our mission today is to cut right through that noise. We want to give you a clear roadmap. The 10 most critical AI concepts, the ones that really form the foundation of modern AI engineering. Think of it like we're building the AI engine piece by piece. First, the fuel, how it's prepared, then the actual motor, and finally how we specialize it and keep its knowledge fresh.
Right. And mastering these fundamentals, well, lets you move past the hype. You can start communicating confidently, make informed decisions. So let's start right at the bottom, the absolute foundation, the large language model. The LLM.
Okay, the LLM, that's the big picture, the goal. The entire prediction system itself, it's a massive, really complex neural network, and it's trained on just vast amounts of text data. Its whole purpose, basically, is to predict the most probable next token in any sequence you give it.
And a token that's the smallest unit the machine actually works with, like a word, or maybe even part of a word or punctuation.
Exactly right. So if you type in all that glitters, the LLM predicts is not gold. Not because it gets the proverb, the meaning, but because statistically that sequence is not gold showed up most often after all that glitters in the billions of examples it learned from.
Okay, that's the core idea. But here's the thing that gets me. If it only predicts the next token, how does the output seem so coherent, so logical? How does just statistics end up feeling like thought?
That's the mind-bending part. Coherence is basically statistical pattern recognition, just scaled up massively, billions, trillions of times. The model isn't thinking, not consciously, but it's recognized patterns that are way too subtle, too complex for us humans to really track across all that data.
Okay, so before it can even start predicting, the AI needs to actually take in the language, right? Which brings us to the first step in preparing that fuel. Tokenization.
Tokenization, yeah.
Yeah.
It's the process of breaking down that raw input text, whatever you type in, into those distinct pieces, the tokens. These are the numerical units the AI can actually, compute with.
And crucially, modern AI doesn't just split sentences by spaces. That's kind of the key insight here, isn't it?
Exactly. That's the old simpler way. Simple splitting would treat a word like glitters as just one single thing. But advanced tokenization, sometimes called subword tokenization, it might break it down into something like glids, utters.
Ah, okay. That structural split. That seems like a really clever hack.
It really is, because by using these subwords, the AI can capture patterns that repeat, like suffixes ling or ellers or intonation. This lets the model learn about thousands of words that are built similarly really efficiently, even if it's never seen that exact word before. It recognizes the parts.
Okay, so we have the tokens, the smallest pieces.
Yeah.
But the AI needs to understand what they mean.
Right.
Not just what they look like. And that's where the numbers come in. You said vectorization.
Vectorization, yes, this is absolutely crucial. It's the bridge. It converts those abstract tokens into numerical representations. We call them vectors, or you can think of them as coordinates, within this incredibly high-dimensional mathematical space. It's literally mapping meaning to math.
So you could almost visualize it like a giant map, a semantic map. And words like dog, cat, poodle, maybe rabbit, they'd all be clustered really close together in that space because they're conceptually similar.
Exactly. Semantic similarity, how alike things are in meaning, becomes a measurable mathematical distance. The closer two word vectors are on this map, the more similar their meaning and how they're used. So the AI can figure out that car and automobile are basically the same concept, even if they never appeared side by side in its training data. It sees they occupy similar locations on the map.
Oh. Okay, so vectorization turns this abstract idea of meaning into a physical, a mathematical location, a measurable position on a map. That's a huge leap.
It is. Meaning gets mapped numerically. So similarity is just distance, something the algorithm can calculate and work with.
But language is messy. Right. It's ambiguous. We use the same word for totally different things all the time. How does the model know if I say apple, am I talking about the fruit or the tech company? This seems like a big problem. And this gets us to attention.
Attention, yes. This mechanism dynamically figures out that ambiguity. It's really clever. When the model processes the word apple, it mathematically it pays attention to the words surrounding it in the sentence.
Ah, so it's looking back at the context it just processed, the words nearby.
Precisely. If apple shows up near words like shares or revenue or iPhone, the attention mechanism gives more weight to those connections, and it effectively pushes that apple vector towards the company cluster of meanings on our map. This was a huge breakthrough. It came out around 2017. It's a major reason why modern AI responses feel so natural and context-aware. It lets the model kind of read between the lines.
Okay, so attention is like a dynamic focusing lens. It uses the context of nearby words to resolve that inherent ambiguity in language.
That's a great way to put it. It contextually focuses to figure out the intended meaning.
Now, thinking historically, to teach an AI anything, you used to need what's called supervised learning, which meant like armies of people manually labeling massive amounts of data. This is a cat. This is not a cat.
Yeah.
Super expensive. Took forever. The scale we see today, with models trained on the whole internet, that would have been impossible.
Right. Utterly impossible. That data labeling was a huge bottleneck, and it was shattered by self-supervised learning, SSL. With SSL, the AI essentially creates its own training tasks. It uses the immense amounts of raw, unlabeled data that's already out there, like all the text on the web.
So the internet becomes this giant free textbook, and the AI makes up its own homework questions from it.
Exactly. It takes a sentence, maybe masks out a word, and asks itself, okay, what word most likely fits here?
Right.
Or it tries to predict the next sentence in a paragraph. It uses the inherent structure of the language itself as the supervision signal. No humans needed for labeling at that stage.
That shift, SSL, allowing models to learn from basically the entire internet without labels. How critical was that? Was that the key to getting models like ChatGPT?
Oh, absolutely critical. Foundational, even. SSL provided the massive and crucially cheap data scalability. That's what let these models grow to the enormous sizes they are today.
Okay, now we should probably clarify something folks often mix up, the difference between an LLM and a transformer.
Yeah.
People use them interchangeably sometimes.
Right. So the LLM, as you said, is the goal. It's the whole functioning system that predicts the next token. The transformer, that's the specific architecture. The algorithm, the engine design, that makes the LLM work.
Precisely. The transformer architecture is what's under the hood. It's defined by its layered structure and its heavy reliance on that attention mechanism we just talked about. It basically stacks multiple layers of attention mechanisms and neural networks on top of each other.
So it's almost like an editing process. The input goes through the first layer, gets a basic understanding, then layer 2 looks at that output, maybe catches more complex things like sarcasm or implications between sentences. That's a good analogy. That stacking is what gives the model its power. Each layer refines the understanding built by the previous ones. It moves from just surface-level word meanings to understanding deeper relationships and context.
And are all the big, modern, state-of-the-art LLMs, are they all built using this transformer architecture now?
Pretty much, yes. Right now, the transformer is the dominant, most powerful, and most common engine design choice for building these large language models.
Okay, so you have this incredibly powerful generalist LLM built with a transformer. It knows about history, science, can write code. But what if my company needs an expert on, say, our very specific internal HR policies, or a specialist for analyzing niche medical research papers? The general model probably won't be perfect. That's where fine-tuning comes in.
Exactly. Fine-tuning takes that powerful, pre-trained base model, the generalist, and specializes it. You give it more training, but this time with highly specific data relevant to the task. Often it's in the form of question and answer pairs. You're tailoring its behavior, its style, its knowledge for a particular domain.
So it's less about teaching it brand new facts about the world, and more about teaching it how to act in a specific role, like the right tone, the right level of detail.
That's generally the main goal, yes. For instance, if you want a really helpful customer service AI, you'd fine-tune it by showing it examples of great answers. You reward it for being direct, empathetic, helpful, and you penalize it for giving vague or unhelpful responses. And, full disclosure, I still wrestle with prompt drifts sometimes, trying to get a general model to consistently stick to a specific persona or style without fine-tuning. So that dedicated specialization is often really essential for reliable performance.
Right. So fine-tuning is primarily about shaping behavior, getting the tone right, drilling down on specific domain language and style. Consistency is key.
That's it. Behavior and tone are usually more central than adding vast amounts of new knowledge. Now, if fine-tuning is like sending the AI to grad school for specialization, few-shot prompting is more like giving it quick instructions right before a task. You include one or maybe a few examples of exactly what you want right there in the query itself.
Ah, okay. So you're not retraining the model. You're just showing it the format or style you want in the moment within the chat box. Like maybe you provide 3 examples of how to cite a source in APA style right before you ask it your actual research question.
Exactly that. The model sees the pattern in the examples you provided, the few shots, and it just applies that pattern immediately to your actual request. It's super useful for quick things. Ensuring consistent output formatting, maybe adopting a specific tone for just one answer, or following a simple rule without needing a whole retraining process.
So when would you choose one over the other? When is few shot enough versus needing full fine-tuning?
Good question. Use few-shot prompting for those quick, temporary style adjustments or format controls, things you need right now. Choose fine-tuning when you need deep, consistent, reliable domain expertise or a very specific behavioral style that needs to persist across many, many interactions and users.
Okay, that makes sense. Now, probably the biggest practical headache with standard LLMs, the knowledge cutoff. The base model was trained up to a certain date. It doesn't know about yesterday's news. And critically, it can't access your private proprietary company data. Retrieval Augmented Generation, RAG, is the solution here.
RAG is the key, yes.
Yeah.
It creates this really clever, dynamic, 3-step pipeline. First, your query doesn't go straight to the LLM. It goes to a separate system, a retrieval system that quickly searches through your own up-to-date documents, your company knowledge base, maybe recent reports, whatever is relevant. It fetches the most relevant snippets from those documents.
Okay, so step 1 is find relevant current info from outside the LLM. Then what?
Step 2. It takes your original query and combines it with those retrieved document snippets, the fresh context. Then, step 3, that whole package, query plus context, gets sent to the LLM.
Ah, so you're giving the LLM the answer, at least the key facts, right before you ask the question.
Pretty much. The model uses that provided verified external data as its primary context for generating the answer. The benefits are huge. It overcomes the knowledge cutoff problem, allows you to use proprietary info safely, and really importantly, it significantly reduces the AI's tendency to just make stuff up to hallucinate because its answer is grounded in those retrieved facts.
Whoa. Okay, that moment of
Yeah.
that real-time retrieval, finding the right snippets from potentially millions or billions of documents and doing it fast enough for a conversation. Imagine scaling that to, I don't know, 1 billion queries a day across massive corporate data sets. That's a serious technical achievement right there.
It absolutely is. It's a phenomenal piece of engineering. It provides that real-time, external, verified context. It grounds the response. It's transformative.
And that intelligent retrieval system you mentioned, the part within RAG that actually fetches the right documents,
Yeah.
is usually powered by something called a vector database, right?
Yeah.
This gets around the limits of just searching for keywords.
Exactly. Traditional keyword search is, well, it's pretty brittle. If you search your company documents for refund policy, it's going to completely miss documents that talk about reimbursement procedures, even though they mean the same thing. It needs the exact words.
Right. Very literal. So how does a vector database do better?
It changes the whole game. Remember vectorization, turning meaning into map coordinates. A vector database stores those numerical vector representations of all your documents. It indexes them based on their meaning, their location on that semantic map. So when you make a query, your query also gets turned into a vector. The database doesn't search for matching keywords. It searches for vectors that are close to your query vector on the map. It searches for semantic meaning, for conceptual similarity.
Okay. So if I search for something like unhappy customer feedback about shipping times, the vector database could find documents talking about delayed deliveries causing frustration or client dissatisfaction with logistics, even if the exact words unhappy or shipping aren't there, because the concepts are close on the map.
That's exactly it. It finds things based on conceptual relevance, not just keyword overlap. It's faster in many cases, and it's definitely conceptually smarter. It finds meaning. So if we sort of zoom back out and connect this all back to that roadmap we started with, we've actually covered the whole stack now.
Yeah, let's trace it. We started with the core engine.
Yeah.
The large language model, the LLM, typically built using that powerful transformer architecture. Then we talked about preparing the fuel for it, tokenization, breaking down the language, vectorization, turning it into meaningful numbers, and attention, giving it that crucial focus to handle ambiguity.
Right. Then we moved to the optimization layer. How do we make it better for specific tasks? We saw the two main approaches: fine-tuning for deep, permanent specialization, like training a medical expert AI, and few-shot prompting for quick, on-the-fly guidance on style or format.
And finally, we tackled how to keep that powerful engine updated and grounded in reality. That's Retrieval Augmented Generation, RJ, which brings in fresh external knowledge. And RJ itself relies on the semantic searching power of the vector database to find that relevant knowledge quickly.
Those 10 concepts, that's really the core vocabulary of modern AI engineering. You now have this mental model, this picture of how all these essential pieces fit together, how they interact to create these incredibly complex systems we see everywhere, from chatbots to scientific discovery tools.
And really, our encouragement to you, the listener, is to start using this vocabulary. Start thinking in these terms. Understanding these building blocks gives you the confidence to cut through the noise, to participate meaningfully in discussions, to ask better questions, and ultimately to make smarter decisions about how AI is used.
Yeah, this knowledge really is the difference between just being an observer of AI and being someone who can strategically understand and leverage it.
Okay, so here's a final thought, something maybe to chew on after this. We've talked about how these concepts, tokenization, vectorization, attention, the transformer, let AI master the complex patterns of human language. But what happens when we take these exact same pattern-finding mechanisms, this whole stack, and point them at completely different kinds of data, not language? Think about the complex structures in biology like protein folding, or the patterns in financial markets, or material science, or even theoretical physics. What new insights might emerge when this powerful pattern recognition engine gets applied to domains far beyond just words? That's something to think about.